Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hi, everyone, and welcome to the third webinar in our quantum computing workshop series. These workshops will lead up to the Future Leaders in Quantum Hackathon, or QC for short, which will happen in mid-May. This hackathon is co-organized by International Telecommunication Union and the Quantum Coalition, a global student-led network of quantum computing clubs. You can pre-register for QC Fleek and check out recordings of past workshops on the AI for Good website, and be sure to stay tuned for more updates and upcoming quantum computing lectures. Today's workshop dives into how quantum phenomena can be used to solve problems and what kinds of advantages this phenomena offer. I'm excited to introduce today's speaker, Dr. Robert Huang, a senior research scientist at Google Quantum AI and an assistant professor of theoretical physics at Caltech. Over the past few years, Dr. Huang has made groundbreaking contributions to quantum machine learning, helping us better understand which tasks quantum and classical devices are best suited for. Thank you, Dr. Huang, for joining us today. The floor is yours.
Thank you so much for the introduction. I'm very glad to be here. Today, I'll be talking about a new work done by me, Richard Allen, Francesco Machado, Isaac Zhang, and Sun-Won Choi on quantum computing and hence sensing, where I will be talking about how a quantum computer can lead to new advantages in various sensing tasks. So as we all know, a central goal of science is to learn how our universe operates, from the most microscopic level to astronomical levels, like understanding atoms, molecules, viruses, to understanding black holes, stars, planets, etc. And an important point or an important instrument that allows us to understand how our world operates is by creating powerful sensors. From microscopes, telescopes, to more modern technology, such as utilizing LIGO as an experiment to help us better understand how black holes interact with one another. So today I'll be talking about some of the new advantages that we can establish in this ground. So before diving into that, I would like to first start out by talking about how current experimentalists try to learn about our universe. So what scientists currently do can be modeled as the following. One can think of it as a conventional experiment. One can also think of it as having a classical AI agent that try to learn about the world. So such a learning agent, a classical one, can learn about our world by receiving, processing, and storing classical information. The classical information can come from doing measurements, come from doing experiments. One can then process these classical information using classical computer to do data analysis to better understand the pattern that we obtained from these measurements and experiments. We can then create classical models like a neural network or some other type of representation, which can be stored in a classical memory. And together, by utilizing these capability, we can try to learn about what's happening out there and try to better understand our world. So while this has been what physicists and chemists and all scientists do for the past many centuries, in the upcoming century, we believe that by creating quantum technology, we can move beyond this paradigm and enter a paradigm where we can conduct quantum-enhanced experiments. One way to think about this abstractly is that by utilizing the entire suite of quantum technology, combined with classical AI or classical intelligent agents, such as humans and neural networks, etc., one can imagine in the future we would have these quantum AI agents that can learn about our world by receiving, processing, and storing quantum information. So the quantum information can be received utilizing quantum sensors, processed using quantum computers, and after that, we can store some quantum model or some quantum data in the quantum memory, such that by utilizing these quantum capability, we can hope that perhaps one can learn much better about our world and make more accurate prediction and see things that conventional experiments that classical AI agents do will be unable to see. And hence, given this dichotomy, one can ask the following question. In what scenarios can these quantum learning agents that can utilize the entire suite of quantum technology obtain meaningful quantum advantage in learning about our physical world over these classical learning agents that can only obtain information about our world in a purely classical form? And that's going to be the main topic of my talk. And roughly speaking, the talk would be separated into the following three parts. The first, I will start by talking about some of the background. What do we know about the quantum advantage in learning from experiments? And where should we go from here? And then after that, I would dive into an application that I've identified on sensing classical field and talk about a new quantum algorithm that allows one to learn much faster than classical learning agents. And then finally conclude with various advantages that we can rigorously show in this setting. So let me begin with the first part on the background. So over the past several years, we have a series of work that have established large quantum advantages in learning from experiments, such as in predicting a huge number of incompatible observables, to uncovering symmetry in unknown physical dynamics, to learning approximate model of many-body dynamics that happens in natural systems. In all of these settings, we were able to show that a quantum learning agent can yield an asymptotically large quantum advantage over a classical learning agent. For example, one can prove that in order to predict a large number of observables, quantum agent only require doing exponentially fewer experiments compared to classical learning agents. And similarly, also for uncovering symmetry, learning dynamics, etc. However, despite all of these theoretical development, a downside of these advantages is that it essentially focuses on quantum learning problems. So in order to prove these large quantum advantages, we need to consider problems where we are trying to learn some quantum many-body systems. And the many-body system must have certain quantum mechanical behavior, for example, large amount of entanglement, etc., in order for some of these quantum advantages to be established. And as a result, while it is nice that we can prove these exponential quantum advantages in various learning problems, they will be limited in the application scope. Because in all of these advantages, we are trying to focus on understanding the quantum world. However, as we all know, our world is mostly classical. And hence, if we wanted to get quantum advantage in a wider set of regimes, not just for specialized chemistry or material science kind of task, then our hope is that we would like to establish large quantum advantage in more classical problems. And hence that raises this question of whether we can do so. There are some more classical learning problem where we can prove quantum advantage. So far it has been relatively challenging to do this. There was a lot of hope about a decade ago where people have created various quantum algorithms for solving classical data analysis problem. But throughout the past 10 years, people have started to develop better and better classical algorithm, and we're able to show that actually in some of these tasks, the quantum advantage people were hoping for actually do not exist. And hence the hope here is that we can find certain classical looking problem with wide range of application such that we can also prove that the quantum advantage exists, irrespective of whether in the future someone comes up with an even more clever classical learning strategy for solving such task. Even when someone comes up with one that is better than all the classical methods right now, they will still fall short of achieving the performance of these quantum learning agents. And while there are a lot of classical learning problems, what we found in this recent work focuses on the task of sensing classical field. So one can imagine that the real world would essentially pass out all kinds of different signals. For example, molecules, when it's vibrating, it will generate, say, electromagnetic field. A planet would also have electromagnetic field that can be detected on Earth if we build extremely good telescope. On the other hand, when two black holes, for example, are merging with one another, it would also generate space-time ripple that, despite being very, very weak, can still be sensed on Earth. So by analyzing and sensing all of these different field signal that come from these perturbations in classical fields, we can try to better understand and create powerful sensors, create powerful instruments that allow us to better understand what's happening in the physical world and to better see and build models around it. So the typical setup in sensing classical field is really like this plot shown here. There's some object of interest. We generate a field. It could be an electromagnetic field. It could be gravitational field. It could be all kinds of different field that we can try to detect using a sensor. And in this setting, we can consider having a classical computer that can control the sensor and try to learn about what's happening versus having a quantum computer, a quantum learning agent that can control this sensor to try to learn what's happening. Broadly speaking, sensing classical fields has a wide range of different applications, from probing material properties to observing merging black holes, detecting dark matter, understanding weak light field, or even detecting brainwave, etc., can all be casted as a problem about learning and sensing classical field. So given this wide range of application that we can have.
Excuse me,
Yeah.
Dr. Huang, just a quick question about the quantum advantage. You mean the computational advantage from the complexity theory point of view? Is that what you mean?
Uh-huh. Yeah, so at this current stage, I'm not restricted to anything. So it could be computational advantages if we can find one. But actually, as I will show later, the advantage will be information theoretic, in a sense that we don't need to make any assumption about computational complexity, but we will be focusing on the sensing time. So in order to detect the field, in order to sense certain property of the field, what is the time it takes to do so? And the advantage we'll be looking at will be about the minimum sensing time that can be achieved by having quantum agent versus classical. And in that case, the time is not the computational runtime, but how long it takes for the sensor to be out there and to be detecting this field. So that will be the main figure of merit that we will be focusing on later, because in that case, we can actually prove things without relying on any assumption. Whereas most of the time for computational advantage, we have to rely on certain assumptions, which may or may not be true.
Okay, thank you.
Yeah, that's a great question. So, so let's look at a few standard sensing task that arises in this broad framework where we try to sense classical field like EM field, gravitational wave, etc., coming into our sensor. One of I would say the most simple task, the simplest task for sensing classical field in the sensing literature is known as DC sensing. DC basically just means it's a static field. So formally speaking, it means that, let's say, we're trying to sense some magnetic field. So either there's a small magnetic field of strength B, so think of B as being very small, or there's no field. So in this case, we're trying to distinguish the two cases. So one can think of this as either there's an object there that can emit a very weak magnetic field, and we would like to detect that to see if the object is there, or the object is not there, and hence there's no magnetic field comes in, and hence we would say, okay, things are absent. So in this case, in the simplest form of DC sensing, we're just trying to detect whether there's a weak field coming in or there's no field coming in. So in this case, suppose that our sensor is a spin. It's a sensing spin. Think of it as a single spin that will be affected by this field coming in. So we all know when the spin is being placed in a magnetic field, it will start rotating depending on where we place it. So let's say the magnetic field is always in the z direction. So it points in the z direction. So now if we put the spin to be pointing in the x-axis, along the x-axis, then it will start rotating. But if we place it in a z-axis that is parallel to the field, then it will not be rotating. But more broadly speaking, or more formally speaking, one can write down the dynamic by considering this Hamiltonian h of t. So it's a single spin Hamiltonian that we consider the spin to be spin 1/2. So it can be written out as b of t, which is either just 0 or a small value b multiplied by the Pauli z operator, capital Z. So when the field is present, like there's a small weak field, and if we place a spin to start out as a point as a direction pointing orthogonal to the field, it would start rotating. But if there's no field, then it would not rotate. So for the simplest task, over the past many decades, people have figured out what is the optimal time it takes to detect whether the field is present or not. And it's given by 1/b. And this optimal scaling has essentially spawned the entire field of quantum sensing, where people try to create quantum state, try to put the spin in a certain form, such that this 1/b can be achieved robustly. However, I would say that in order to achieve 1/b scaling, there is a very simple protocol that one can do it. And the protocol essentially looks like the following. So think of it as we start out by placing the sensor to be pointing in this direction. And let's say the field is going outside of the plane. So the z direction is going out from this slide. So when the field is present, the spin will start rotating. But when the field is absent, the spin will not rotate. So what essentially happens after a unit of time, it becomes like this. And slowly, after more and more time, we can see that when the field is not present, when the field is absent, the spin will just not be moving. But when the spin is present, it will start rotating slowly. And at around the time pi/b, so roughly scaling as 1/b, if the field is weak, then this is going to be a very long time. We can see that the spin is now rotated to a direction that is opposite from the starting direction. So now at this point, when we perform a measurement, measuring in the direction based on where the spin starts, we will see that when the field is present, it will be in the opposite direction compared to when the field is absent. And hence, with time 1/b, we will be able to accurately detect whether the field is there or the field is not there, hence solving the simplest task of DC sensing. However, one should note that when there's multiple when there's multiple spins, then in order to achieve the optimal scaling, one actually has to create like a GHZ state that entangles everything. But in the case, and then after you create a GHZ state, it falls back to very similar to this protocol. Like one just run this in order to detect it. So in general, one should think of the optimal protocol as we're just letting the spin evolve and at the end just measure. And that would give the optimal scaling of 1 over b. And one can also prove that this is optimal. One can show that there's no way that one can achieve a faster scaling, even when we put a quantum computer on the side to control the sensor in a crazy fashion. There's no way to outperform this 1 over b scaling. That is the best. So in a way, for the simplest task of DC sensing, everything is solved. There's nothing more to do from a more theory standpoint, because in this case, the optimal scaling is known, it's very easy to achieve, and that's it. However, one would argue that actually in a lot of applications that I mentioned, like detecting EM field, electromagnetic field, detecting gravitational wave, it actually doesn't fit this framework. Like when there's a gravitational wave coming in, the field that we're sensing is going to be oscillating through time because it's going to be, say, like a cosine wave coming into the Earth instead of just a single static object. And the same also holds for light. When there's an electromagnetic field, like a light field coming into Earth or light field that we're trying to sense, it will be oscillating. It will not just be static. And as a result, in a lot of these applications, we are actually going to encounter the second simplest task known as AC sensing. So in this case, the goal is still try to detect whether there's a field or there's no field. However, as we can see, when there's no field, it's still B of t equal to 0. But when there's a field, it will be oscillating from positive to positive to negative, and so on, with an unknown frequency omega. So for example, if you're trying to detect dark matter, it will actually generate signals that will be fluctuating, oscillating through time in an unknown frequency because it depends on some of the new physical properties of dark matter, which we don't know. Like it's a new physics and we have not ever measured them. And as a result, we don't know what the frequency is. And in various other applications, like when the black holes is merging in some way and based on the properties of these black hole, the space-time fluctuation will be oscillating in some unknown frequency. So broadly speaking, we don't have a knowledge of what the frequency is. We might have some sense on where the range is. So there will be some minimum value to some maximum value. It could be spanning across multiple orders of magnitude. So this delta omega, which is this interval, could be quite wide. For example, if it's spanning across visible light to radio wave, that would be 10 to many orders of many orders of magnitude that we need to search over in order to detect whether the field is present or not. So as I have claimed, most of the field that we encounter in practice, these classical fields coming into the sensor, will be oscillating field. And as a result, we will fall into the second simplest task that is not strictly covered by the previous one. Intuitively, one might feel like, maybe this AC sensing is not that different from DC sensing, as I will talk about some of the protocol that people do. But this is a different task, and one need to do some modification. So let's say we continue to use the same protocol for sensing a static field, and we can see what happens. So here I'm drawing this purple line correspond to the field oscillating from being positive to negative to being positive to negative. So when it's positive, it means that it's going to, let's say, rotate the spin clockwise. But when it's negative, it's going to rotate the spin counterclockwise because the field is oscillating positive to negative. So you can think of it as sometimes pointing out of the screen, sometimes pointing in of the screen, and just keep oscillating back and forth. So if you start out with the spin pointing this direction, after this time, it will be rotated a little bit. On the other hand, when the field is absent, it will not be rotated. But then after a same unit of time, because now it's the field is negative, it will be rotating back to become this direction. And as we can see, the dynamics of this sensor is that in the case when field is present, it would just be oscillating along the direction of where it started. And as a result, even when we have put the sensor out there for a very, very long time, and then when we measure, we will still not see much difference between when the field is present versus when the field is absent. And hence, a standard DC sensing protocol would not be able to solve AC sensing. So right now, the best strategy that people do in experiment is the following. They essentially apply some rotation within within this time flow in order to accumulate signal. So what do I mean by that? So at the start, it would just let it evolve. But now after it evolved for some unit of time, what it would do is it will do a pi pulse. The pi pulse just means I'm flipping this. So flipping it based on, I'm considering this as the axis, I'm just flipping the spin to the other side. And so now while the signal is going to start, like the field is going to cause the sensor to be rotating counterclockwise. So note that the previous step is rotating clockwise. And now we also know previously when it's rotating counterclockwise, it would be rotating back to the initial point. But now if we flip it and rotate it counterclockwise, it actually now goes to this position, which then after we flip it again, we will see that from this time point to this time point, actually we have accumulated signal fully. So now if we do it again, now it's evolving clockwise, flip it, evolve counterclockwise, flip it back. We can see that unlike in the standard DC sensing protocol, it would just be oscillating at the initial direction. In this case, when we're applying these flips in the right frequency, we can actually accumulate signal. And as a result, at around time 1 over b, just similar to previously, the spin will now be flipped to the other side. And hence, when we now perform a measurement, we will be able to detect accurately whether the field is present or whether the field is absent. So that is what experimentalists do in trying to sense this oscillating field. But note that this actually requires us to know what the frequency is. If we apply these pi poles at a certain frequency, what essentially happens is that when we do this measurement, the measurement outcome that we get will only be sensitive, or we will only see this like difference between pointing downwards versus upward when the frequency of the unknown field matches with the frequency of how we're applying this flip. If the frequency of the unknown field, let's say it's omega 0, and we're applying frequency based on omega 2, that is, let's say they're very different, then we're not going to see anything. We're still going to see that the field is, the spin is going to oscillate at the starting location. And hence, when we perform measurement, it will be very similar to like this, like the DC sensing protocol. So in this best existing protocol, one has to guess what the frequency is in order to match it, like match it with the true unknown frequency. And if one correctly matches it, then one could see a response, one will see something. But if it's not matching it properly, then we will not see anything, and then it will fail. So the best existing protocol in order to handle the case that there's multiple frequency or handle the case that the frequency is unknown and there's this window of frequency, one essentially have to sweep over all the distinct frequency or all the sufficiently distinct frequency. And by a rough back-of-envelope calculation, one or as well as a more detailed experimental calculation, one can show that the effective number of frequency that we need to consider is roughly of the size delta omega over b. So delta omega is the range of the frequency, and b is the field. So if the field is strong, then the number of effective frequency that we need to go through is not too many. But if b is very, very small, then actually the number of frequency that we need to screen through will be large. And the reason that there's this additional 1 over b come from the fact that this procedure takes time 1 over b. And as a result, there is this scaling. And also one can do like a unit test. Basically, frequency and the field strengths have the same unit. And hence, when we divide one another out, we will get something that's unitless, which is what a number should represent, would be something that's unitless. And hence, together, the best existing protocol has a sensing time that scales like this. 1/b come from each frequency. So for each frequency, one would need to run the experiment for 1/b time, and then one would need to loop through all the different frequency, giving rise to this scaling of delta omega divided by b. So that's the total sensing time required by the best experimental protocol for sensing classical field. But then one could ask the question, so it sounds nice that this protocol seems quite relatively simple, but at the same time, it feels challenging to go beyond this. And that's why over the past many decades, this is what people settled on. Like when people try to detect AC field, this is what people do. But one can ask the question, is this really the best protocol? Like it's the best known protocol, but is this truly the best protocol in the entire world?
Yeah, just a quick question about notation. Like, what
Yes.
exactly does C-link represent here? Uh,
Yeah. So it's really just the ceiling function. So for example, if delta omega, like this frequency range, is very small compared to the field, let's
oh,
say the field is a unit, like a 1, but the frequency range, like let's say we have a lot of prior knowledge, so the frequency range is 0.1, then in that case, when we divide it out, it would actually be 0.1, right? But we actually need to take a ceiling because we still need to check at least one frequency in order to detect the field. And hence the ceiling just represents this phenomenon of we at least need to check one. So we need to make it a ceiling function. So it's yeah, taking a floating point number or just a real number and turning it into an integer.
okay, thank you.
Yeah. And while people in, say, computer science or information theory, we love to think about what is the optimal scaling for achieving a task. For experimentalists, that's not usually the way they think about things. So they settle on this because they think this seems very reasonable and they can do it, and also feels like this is the best. And hence, um, people often think that this is the best scaling that we could get. But in in reality or in theory, that's not necessarily the best because no one has ever proved a lower bound, a fundamental physical limit that says in order to sense a oscillating classical field, this is required. So this is just an upper bound on the sensing time that one could achieve, but never a lower bound. And hence the true optimal time it takes to detect an oscillating field remains unknown. And recall that for achieving DC sensing, it gives rise to this entire field of quantum sensing. One could also ask, could obtaining the optimal scaling for this give rise to a new concept? And that is going to be the main claim of and one of the main claim of our work is that in order to achieve this optimal scaling, we need to use a quantum AI agent or a quantum learning agent that sits on the side to control the quantum sensors in a quantum fashion coherently and run some advanced quantum algorithm in order for the optimal scaling to be achieved, in order to get the best scaling for AC sensing. There's quite a large gap between having a quantum computer controlling sensor versus classical computer controlling sensor um, with respect to this task. So that's going to be what I'll talk about later. So first, I would like to dive into our algorithm to describe what our algorithm look like. And then I will talk about the advantage in the final section of the talk. But before diving into that, one can first ask this question. Suppose I have a sensor that have a quantum computer that sits on the side to control it. What is the most general model of all the things that could be done by having a sensing strategy enhanced by quantum computers? And theoretically speaking, one can write out the output state of the most general quantum computer enhanced sensing protocol as the following. So initial state, once you think of it as this 1, corresponds to the sensor. This little n corresponds to the quantum computer, the qubits in a quantum computer. So there's n-qubit quantum computer that controls this one single spin sensor. And what one could do is first, we start out with an all-zero state, utilize some quantum circuit to untangle the sensor and the quantum computer. And now the sensor will be evolving under the external field. So this identity is acting on the quantum computer. So nothing happens to the quantum computer, hence identity. But the sensor will be evolving based on the field that was acting on it. So this is essentially just represent like a rotation. If we integrate out b of t multiplied by Pauli z operator on the first qubit and then exponentiate it, that corresponds to the rotation that's applied to the single spin sensor. And here this b of t is the unknown field we would like to sense. And after doing that, we will go back to run a quantum circuit across the quantum computer and the quantum sensor. Let the sensor evolve based on the external field, apply a circuit onto the quantum computer and the sensor, and just keep repeating this process for multiple rounds. But note that the protocol gets to choose how many rounds is repeated. So capital J corresponds to how many rounds. And this time interval corresponds to what is the interval where the sensor gets is rotating under the external field. So T0 corresponds to time equal to 0. T1 corresponds to the next time point, and then T2, T3, and so on, until the very end, we will get capital T. And capital T is the total sensing time, because that essentially counts, or that essentially corresponds to the time it takes for the sensor to be interacting with the external field. And that's the total sensing time that we would like to minimize. So recall that previously, the protocol, this putting in this pipe pulses can also be casted this way. In that case, there's no quantum computer sitting on the side. But every time we will apply like a flip, like an X gate. So this UJ just corresponds to an X gate acting on the single qubit sensor or single spin sensor, which we will undergo some evolution. We will apply a flip, undergo some evolution, apply a flip, and so on. So this kind of matches with what we have previously. But now it's much more general because we now have a quantum computer that sits on the side that can control the sensor coherently. So let's see what happens. So let's see what one can try to utilize this model and try to figure out what is the optimal scaling. So in order to understand this, we're going to utilize a concept that people use in quantum computing a lot, which is known as oracle separation or the oracle model. So recall that an oracle basically means the following. An oracle is just some function that we don't know. It's some unknown function, the oracle. And what one could do classically is one can specify some input. Like in this case, it's a bit string of n bits, so an x. And then the oracle will spit out a single bit and give it back to the classical computer. On the other hand, in quantum oracle complexity theory, people would study what kind of advantage one could get when we have a quantum computer that can access the oracle coherently. So for example, it can put in the inputs in superposition, possibly entangle with itself, and then retrieve the output coherently. So this gives rise to this most well-known quantum advantage known as oracle separation. A lot of the well-known quantum algorithm and quantum speedup actually come from this setting, such as Simon's problem, such as Grover search, where we try to get so in Grover search, we get a quadratic speedup in finding a marked element. In Simon's problem, we get an exponential quantum speedup in figuring out an unknown period. But one of the common complaints people have about oracle separation is that this oracle is really an idealized model. It's really like an oracle that is a pure black box, and we can access it coherently. And it's unclear where these oracles come from. Like in practice, in computational problems, we don't have oracle that are black box. These oracles are going to be implemented by some quantum circuit that we know all the details about the circuit. but we forget about the details and treat it as an oracle, which is quite unrealistic. However, if we think back on sensing task, we can see that we can really treat physical world as an oracle because we don't know how the physical world is operating. We don't know some of the properties, and that's why we wanted to do some experiments to try to learn about them. So we can think of the physical world as this oracle that provides some answer into the sensor. And then the quantum agent or the classical agent can try to access the sensor in order to learn about this oracle. So the conceptual idea for our protocol is that we're going to treat the classical field coming into the sensor as an oracle, similar to this case. However, the challenge is that we need to build out a quantum oracle. So usually in oracle separation, the separation comes from, in the quantum agent case, it gets access to a quantum oracle, which whereas in the classical agent, it gets access to just a classical oracle. And getting access to a quantum oracle is much more powerful than getting access only to classical oracle. And that's why one can get huge advantages, like in Simon's problem, or some quadratic speedup in Grover search. It's all because of having quantum oracle. So the key idea or the conceptual idea is we wanted to create a quantum oracle that allows a quantum computer or a quantum agent to access, to query in order to learn much faster than classical agent, which cannot create a quantum oracle. So how do we do that? So recall that in this most general formula for the output state, essentially we can think of this part of the circuit as an oracle. So that is how the external field, the external classical field, is exerting forces onto our sensor. So it's a single qubit operation that's happening. So in the sensing task, we're trying to distinguish between either it's b cosine omega t plus phi or it's just 0. So in a way, one can think of this classical field as an oracle. But it's a strange looking oracle because it has two unique features that is very different from how people in oracle complexity theory think about the problem. The first is that this is a single qubit object because it's just acting on the spin sensor, the single qubit spin sensor. And second, a very important feature is that it's time varying. It's varying in time. So as time goes on, this oracle will change. Whereas in normal oracle query complexity theory, people treat oracle as a multi-qubit object that is time stationary. Every time when we query it, it will be the same thing, and it's not changing through time. So a very important aspect of getting this new quantum advantage is through digitization. Essentially, what we wanted to do is we wanted to turn this analog time-varying field signal into a digital quantum operation. More precisely, we wanted to turn it into a well-known oracle problem. So for those of you who are familiar with Grover search, this oracle shown here should be pretty familiar. So what we wanted to do is that we wanted to essentially turn the sensing task into an oracle problem, into Grover search. So what is this oracle OK shown here? This is basically the Grover oracle. So it essentially says, essentially one way to think about this is we were going to divide out the entire frequency range into small bins of different frequency window. And if the unknown frequency lies in a certain window, then we're going to consider marking that bin. So in that case, one can think of it as this is a diagonal operator where there's a bunch of different classical configuration corresponding to different frequency bin. And if omega lies in the kth bin, then at the kth bin, we will have a -1 phase, but all the rest will have a +1 phase. And that is the well-known Grover oracle. Versus, on the other hand, when there's no field, then nothing is marked. So it's just +1 for all the frequency bins. So the sensing task of distinguishing between having a field or not, if we do this, if we are able to create a quantum oracle out of the classical field, then suddenly we can cast it into a Grover search problem where we are trying to distinguish between either it's the Grover oracle with some marked element, or there's no marked element. So that's going to be the main idea that we are going to be looking at, is we're going to consider doing a bunch of operations. Think of it this way, doing a bunch of operations, starting with some quantum circuit, do some field, kind of let the sensor be affected by the field, do some quantum circuit again, and keep repeating this process for multiple rounds. And then at the end, run the quantum circuit again, such that together, this whole block of operation will become very much this Grover oracle. So that is what we call digitization, where we try to turn an analog time-varying field signal into a digital quantum oracle. So this is like intuitively speaking, this seems doable, but it is surprisingly complex. So running this digitization is not an easy task because we need to essentially turn this single qubit time varying oracle into a multi-qubit time stationary oracle. So there are a lot of challenges, such as how do we turn this varyingness, like it's varying through time. So essentially the signal for like essentially which element we should mark actually is contained in the time domain. And we need to now cast it into the space domain. And that is the key challenge. We wanted to coherently extract information from the time varyingness and placing that into this phase in the spatial domain that essentially labels when we put in certain classical configuration, it will label it with a -1. So due to the time, I would not be able to dive into the digitization too carefully, but I just wanted to go through some of the basic ideas that we utilize. So the first is we're going to use this pi pulse ideas that I talked about. That is how people usually do AC sensing. So it's a very well-known AMO technique. But then we're going to combine it with this quantum computing idea, which is we're going to have a quantum computer that sits on the side. And depending on the state of the quantum computer, we will run the CPMG sequence in superposition. So we're going to run a bunch, like a huge number of different frequency in superposition controlled by the quantum computer. That essentially creates like some kind of response function that look like this, which we need to essentially turn it into a nicer looking function that look like this shown here. And the way we do that is we're going to utilize also again a very well-known technique in AMO physics known as AC Stark shift, which has won a Nobel Prize on. And that allows us to engineer the Hamiltonian into a certain form, which then we utilize a quantum computing technique known as adiabatic path integration. But we are going to do it in a very non-standard way. We're going to consider starting out with having no field, and then slowly turn on the field, and then coming back to have no field. The purpose of doing this adiabatic path is that we wanted to essentially remove the time dependence. So this step is extremely important for turning time varying or combining AC Stark shift and adiabatic path is central to essentially killing the time dependenceness of this problem. So by doing AC Stark shift and adiabatic path, we can essentially turn a time varying oracle into a time stationary oracle, which is a very important part if we wanted to map it into a quantum oracle that is always time stationary. And then finally, we do quantum signal processing to essentially turn it into a digital form. So originally, it would be a continuous analog signal up until this step. So after this, so step 1 and 2 essentially give in sort of like the interaction between the quantum computer and the sensor. So now when the sensor is sensing signal, that signal can be kind of back action and being placed onto the quantum computer. And then step 3 and 4 essentially allows us to kill the time varyingness of the signal. And finally, step 5 allows us to turn an analog signal into a digitized signal by utilizing quantum signal processing. And together, all of these steps allows us to create a Grover oracle out of this time-varying analog field signal. So it kills the time varying part and also digitize it. And then what we can do is we just run, given this digitized Grover oracle, we can just run Grover search. And that will allow us to kind of in superposition, figure out what is the unknown frequency of the field. So now let's look at what are the advantages we can get. So that's the algorithm. It uses quantum computer in a very essential way in order to detect classical field. So what are the advantages we can get? So the first theorem that we prove in this work is that utilizing this QC enhanced sensing, we were able to achieve a sensing time that scales like this. So the 1 over b just intuitively come from the time it takes to check a single frequency. And then also note that this number, this scaling here, is the number of frequency we need to check. And because of Grover search, we get a quadratic speed up there. And together we get 1 over b times square root delta omega over b. And note that this kind of similar to the Heisenberg limit of 1 over b. But in the DC sensing case, where we get 1 over b, we have full knowledge of the frequency. Or in a way, that frequency is 0 because it's time stationary. So in that case, we don't need we have this square root will become equal to 1 and hence reduces to this. But one could ask like, okay, we're just cooking up some random quantum algorithm for solving the sensing task. What is the physical limitation for solving AC sensing? Should the frequency range appear in the fundamental limit? Does there exist some clever algorithm such that even when there's a huge amount of frequency range, like a wide frequency range, we can still somehow quickly pinpoint where it is? Like for example, I might guess that maybe instead of having a square root behavior, maybe we can do some binary search and perhaps get log of the effective number of frequency. Is that possible? And what we were able to prove is that actually there's a fundamental limit where Grover search and Heisenberg scaling combined into this scaling of 1 over b times square root delta omega over b that exactly matches the upper bound that we were able to achieve. So in a way, it's not possible to achieve even better scaling. There's no way to do some kind of binary search. We have to do some version of Grover search, no matter how clever we are in designing the sensing protocol. And also one can see that somehow in the sensing task, the Grover search idea emerges very naturally. And that is the best thing one could do for sensing oscillating field. So going back to this, the second simplest task of sensing oscillating field, we can see that the optimal sensing time actually is this. And then one can ask, okay, so now we can achieve this using a quantum computer that sits on the side. What about having a classical computer? What if I only have a classical computer that tried to achieve this? What is the scaling? So what we were able to prove is that actually what the experimentalists have been doing up until this point is actually also optimal in a sense. It's optimal in the sense that when we're just classical being controlling a quantum sensor, then this is the best achievable scaling. The one that was achieved using the best known algorithm. And note that the divide between these two corresponds to either having quantum computer that controls quantum sensor, which can get this scaling, versus having classical computer that can control quantum sensor, which give rise to this scaling. So one could ask, how big is this speedup? So while in terms of the thing here, it looks like it's just a quadratic speedup, but there is some interesting regime that we can look at where the speedup becomes even more dramatic. So one can look at this case, which we called the strong field large bandwidth regime. Basically just mean the bandwidth is very large, so we don't know the frequency, and also the field is very strong. In this case, one can put in this formula, like put in the scaling. So capital N is some large number, so that is exactly equal to the bandwidth. And we also consider the field to be very strong. There's also some large number scaling as n to the mu. And now we can plot the speed up. So when mu equal to 0, we can now plug it in, mu equal to 0. We get n to the 0.5. And here, mu equal to 0, it's n to the 1. And hence, it's just a quadratic speed up. But now if we plug in something like mu equal to 1/5, so if it's now this is 1/5, we can do a simple calculation. It's just n to the 0.2. And then here, if it's 1/5, it's n to the 0.6. So now it's n to the 0.2 versus n to the 0.6, which is a cubic speed up. So when mu equal to 0.2, we actually get a cubic speed up. And now when the mu is bigger and bigger, we actually start to get large polynomial speed up. But at the end, when mu is roughly at 1/3, we can see that QC enhanced sensing just becomes a constant sensing time, whereas for classical computer controlled sensing, it would still be n to the 1/3. And hence, at the limit, it actually becomes a constant versus polynomial speed up. So what is quite interesting is that here, even though we're basing off of Grover search, because of the additional digitization phase that gives rise to this 1/b scaling, in this strong field large bandwidth regime, we can actually achieve a beyond quadratic speedup, such as a cubic speedup or a quartic speedup or some large polynomial speedup. But I should also note that at the extreme, at the end, what we all get is just a constant versus polynomial speedup. So never a super polynomial speedup. It's always just at most a constant versus polynomial speedup. One can also establish advantage over any quantum Fisher information-based sensing. So the idea of QFI is that we want to enhance the sensitivity under infinitesimal perturbation to the parameter. But as we can see, in order to run our procedure, we need to do digitization. And a well-known feature of digitization is that it actually turns things to be kind of flat that look like this. So when we just perturb the parameter a little bit, we actually don't get any sensitivity. Like the sensitivity is 0. So the procedure that we have actually have QFI that goes to 0. So what's quite interesting is that usually in the sensing literature, people focuses on maximizing QFI, but actually in this AC sensing task, we can show that in order to achieve the optimal sensing procedure, we actually need to get a 0 QFI. And furthermore, we can prove that whenever we try to optimize QFI, try to get the maximum QFI possible, it will lead to a sensing procedure for this task that scales like a classical computer control sensing, which is worse than the QC enhanced sensing that we created. And similar to before, that means when we compare over QFI-based sensing that maximizes QFI at every point, we would also lead to some quadratic or beyond quadratic polynomial speedup. And as a result, we would claim that what is the new kind of idea that arises here is that computational quantum advantages can actually be casted in a new light and lead to fundamentally new sensing advantages that are completely information theoretic. So that doesn't need to rely on any computational assumption. And furthermore, not only our algorithm can be analyzed theoretically, we have also done a noisy simulation using NV centers. Basically, we take this diamond and consider the defects in the diamond, and they're known to be very good sensors. And furthermore, there are nearby defects that we can use as quantum computer. So we can use the defect in the spin1 defect in the diamonds as sensing spin, and use the nearby other type of defect as quantum computer to implement this protocol. And in a realistic physical simulation, we were able to show that under various type of realistic noise, we were able to achieve these new quantum advantages over traditional classical computer controlled quantum sensing procedure. So in conclusion, while previously the sensing literature has been focused on the advantage of quantum sensors over classical sensors, where we can achieve a Heisenberg limit versus standard quantum limit type of speed up by maximizing QFI, which in this case just results in a quadratic speed up. We considered this new notion of having quantum computer that can control quantum sensor and show that by doing so, we can actually get a further speed up over just normal classical computer controlling quantum sensor. In this world, we believe that by considering different kind of quantum algorithm, we will be able to achieve, and this setting actually hosts a wide range of new quantum advantages that remains to be discovered. So towards the end, I wanted to say a few open questions. The first is that it is well known that Heisenberg limit is not achievable when we have noisy quantum sensor. However, a quantum computing enhanced sensing represents a new paradigm that might be inherently very different from the standard like maximizing QFI type advantage. And hence, perhaps some of these new metrological gain, some of these new sensing advantage will still survive under noisy quantum sensor. So that is a very important open direction to be explored further. Another direction is that in the quantum computing enhanced sensing strategy that we have been considering utilizes a logarithmic sized quantum computer to do Grover search. And as we have shown, this can already achieve a relatively large metrological gain. But in practice, for example, in NV center, the nearby defect is just a constant amount. We cannot scale it up. So is it possible that even when we have a constant size quantum computer, or even just a single qubit quantum computer, could that already lead to some large metrological gain? So that's another interesting question to study further. And finally, as we have seen, we can achieve a constant versus polynomial speedup. But is it possible that we can utilize similar ideas, but try to digitize other type of time-dependent signal such that we can achieve some newer and even bigger metrological gain? For example, can we utilize some of the other oracle separation that hosts superpolynomial advantage to achieve some of these, to achieve superpolynomial advantage over sensors controlled by classical AI when we utilize sensors controlled by quantum AI. And that's it for my talk. Thank you so much for listening.
Thank you for the talk. I really enjoyed it being like physics centered. Yeah. I have a few like, questions slash remarks.
Yeah.
I think we should have like a little bit of time left. So can you please go to the slide where you showed the digitization?
Yes.
Yeah. Yeah, here, perfect. So, like the question I had is that do we just assume that we can kind of like stop sensing to apply this unitary UJ, or like in the case of a single qubit, if, like in the previous case you showed that it's just an X. Like, can we just assume that we can stop sensing, then apply this like perturbations and continue sensing again, then apply perturbation? Can we just do that?
Yeah, I mean, theoretically, one can assume that the field that we are sensing moves very slowly, and hence the gate that we are applying can be very fast. That's also the typical setting. Like even for the best known experimental procedure that runs this pipe pulses also makes the same assumption. So
Mhm.
currently, when people do AC sensing, one would also have to make this assumption that this pipe pulse can be done very quickly. Kind of like we can stop it and then just quickly apply it and then keep running. But of course, in practice, we can never stop it. Like the sensor will just be accumulating signal simultaneously. So we cannot really like truly stop it and then apply it. So usually what happens is one just try to approximate this. So one kind of ramp up the pipe pulse very quickly and then ramp down very quickly. And in the meantime, the field will still be affecting the sensing spin. So I would say this is more like a theoretical formula that try to consider the ideal setting where it happens. In reality, there will always be everything is ongoing. So the control, so once you think of this UJ as we're essentially applying some control Hamiltonian, and that in its way would actually be kind of intertwined with the field that's affecting the sensor. So in that case, yeah, so this should be thought of as this is just doing it very quickly, so it can be well approximated by a pi pulse. And in a way, that's the only thing, that's the main place where we need to stop it. Like we just need to run CPMG sequence in superposition. And while that seems a bit daunting, actually, it doesn't need to be, it's actually not that daunting. It's because if we consider the quantum computer to be represented as a binary state, then essentially it just corresponds to there will be some qubit that needs to be pulsed at the fastest rate, and then there will be a qubit that is being pulsed at half of a rate, and then the next qubit will be pulsed at a half of that, and so on. So in that sense, when we have this quantum computer sitting on the side, for the qubit that's interacting with the sensing spin, in the kind of the highest frequency qubit, that would just be pulsed in the same rate as the standard CPMG sequence. So what experimentalists are currently doing right now, we're going to do the same thing. But there's this one difference. So here, experimentally, they'll need to do like a single qubit operation, but here we will have to do a two qubit entangling gate. So we need to have the nearby computing sensor to be interacting with the sensing qubit or quantum computer qubit to be interacting with the sensing qubit kind of closely in order for this to happen. But beyond step 1 and 2, all the rest are actually like for example, this one is just saying, oh, we need to be slightly off resonance. So that's similar to before. That doesn't change much. The adiabatic path also just basically means we need to apply some single qubit gate to essentially turn on the field or turn off the field exposure. And this digitization phase is also done quite easily. And this doesn't need to be done very frequently. Just after some time, after accumulating signal, we do some quantum signal processing, and then we go back. So the only instantaneous kind of operation is very much the same as the best known experimental procedure for doing AC sensing, which is this kind of pi pulses. We need to pulse it in the right frequency in order to accumulate signal. And and that's pretty much it for, I mean, for the protocol that we're presenting, that's pretty much it. But and that's also why we were able to like do these numerical simulation where we assume like all of these. So we don't assume that we need to turn off the field. We just kind of let the computing spin be interacting. As long as they have some interaction, like one can write it out as a purely Hamiltonian form. So as long as they're interacting with some Hamiltonian like two-body interaction term, then they actually also simulate the CPMG sequence. So that's how we were able to do a realistic simulation using MV centers in order to do it is because of that. But more broadly speaking, one can imagine that there are some other novel procedure where one might need to really run some crazy quantum circuit instantaneously. Then in that case, one would need to think twice on how realistic and how experimentally friendly that would be in order to do it. But in this case, the experimental capability is not too different from just the standard AC sensing procedure people have.
Okay, thank you. And the very last question is like about the proof of optimality. Does it just stem from Grover's the optimality of Grover's search, or it's like uh, so basically like, what was the like a sketch of a proof of optimality of the protocol?
Yeah, so I should say, so note that in Grover search, it assumes this kind of multi-qubit oracle, that whenever you query it, it's always the same, right? And it's very much tailored towards that. But here, there's in a way no such object. Like we just have some time varying signal. Like in a way, the classical field is there, and then the varyingness is always there. So so a priori, it's not clear that it must represent a Grover type speed. Like Grover, it doesn't like it's not a priori clear that a Grover limit is the right limit because one can imagine maybe I could do some binary search. Maybe I can chunk up into two big frequency chunk. One is the left chunk and one is the right chunk. And then for each of them, I just test whether there's a field inside, right? Like if that's possible, then we would get a much faster procedure that can easily distinguish or easily detect field. So in a way, so in order to prove lower bound in this setting, I would say one really needs to dive into this time varyingness, which is not what's present in Grover search. Grover search, every time you query the oracle, it's the same thing. But here, the lower bounds, the physical limit, come from the time varyingness and the uncertainty and the unknown in the time varyingness. So in order to prove the lower bound, we have to kind of embed that into the proof, which is, I would say, a way that's completely different from Grover search. But there are elements that are similar. So in Grover search, how do people prove lower bounds? Is they try to consider for different marked elements, how do things diverge? Like how do quantum state diverge in terms of L2 distance? So here we also track that, like try to understand how do things diverge under L2 distance when we have different frequency. So when there's this kind of time varying signal that comes into my state. So think of it as here we have this output state, and so one could think of this B of t to be fluctuating across different frequency. So essentially we need to look at this object and see as there are different omega that can come into play. How do the output state diverges away from each other and away from when there's no field, and try to capture that L2 distance and try to control their divergence in order to show that, oh, actually, it cannot diverge too fast. It will actually diverge quite slowly. And the wider the frequency range is, the slower it will diverge. And as a result, one can establish that lower bound. So I would say deep down on that mathematical level, we are capturing kind of like this L2 divergence, which we're not just using Grover search, but using a lot of different query complexity proof. But other than that, one will have to really tailor into analyzing this time varyingness. That is an essential part of the proof to establish the lower bound. So even though we called it a Grover-Heisenberg limit, the proof is very different. Like I don't think Grover search proof will just give rise to this because, yeah, of various differences.
Okay, thank you so much for your talk.
Yeah, thank you so much.
Yeah, thank you. Bye, everyone. Thank you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.